All right, so this is the introduction to the bungee jumping lab that we'll be doing during the midterm testing period. So in this lab, what you'll be doing is taking a weight of some sort, and you will be making your own bungee jumping apparatus so that whoever gets closest to the floor here from the third floor of the building, when the weight is attached to your bungee jumping system, will earn the most points. So the way we do this is you'll be taking some sort of weight and you will have to hook it up to a series of rubber bands. Now these rubber bands, obviously we don't have 30-foot long rubber bands that we can deal with, so you'll need to link them together. And when we link them together, the K, the constant, the elastic constant of how they stretch, it changes. So typically if we have one constant, we would call it K. But as you link them together in series, one after another, so if you have a loop here, and then a loop, and a loop, and a loop, and a loop, they follow the rule of the equivalent. The 1 over the equivalent is equal to the sum of 1 over K1 plus 1 over K2 plus 1 over K3 and so forth. And we can just keep on going however many rubber bands that we have. But to make this more simply, then the equivalent spring constant is going to be equal to K over N. Excuse me, where N is the number of rubber bands that we have. So that takes care of part of it. And if we look at our system right here as a whole, we see that when we're at the top, it's all gravitational potential energy. And as the weight falls, it becomes all spring potential energy when it gets down at the bottom. So whatever gravitational we started with up at the top, when the weight stops all the way at the bottom, it now becomes all spring potential energy. And there's kinetic in between, but we don't have to worry about that kinetic because it's stopped at the speed is 0 at the top, and the speed for that instant where it's fully stretched is also 0. So there's no kinetic considerations to take into account. So if we look at that, then we have the potential of the gravitational equaling the potential of the spring, or mgh equals 1/2 kx squared. Now what we want to know is we want to find that point where the potential equals the equals the spring. So in that case then we would have 0 is equal to 1/2 kx squared plus minus mgh. And when we have that point, that should be the point right at the very bottom where the rubber band or the whole system as a whole, the weight will get as close to the bottom as you can make it. So that these two terms, the starting potential is equal to the ending spring potential, so that then we are left with then 0, and that will be where we bottom out. Now, we can figure out what the potential is, the starting potential, so we know what this finishing spring needs to be. The problem here is our K. We don't quite know what that K is, and it also affects our X. So we can go through and you could actually figure out all the different N's and all the different K's that you need in order to figure out what is going to get them equal to 0. And that's lovely and that's nice, but you could be there for a long, long time, and it'll take a lot longer than the time that we have. So what we can do instead is we do what's called an iteration, and we can do it through Microsoft Excel. So this has already been completed for you, and here we have just a blank setup where if we look at our blank setup, we can plug in what our K is, and you'll have to determine your K. You'll have a weight, which you'll be able to, again, measure and know that. The height, H, is the height of the drop minus the length of the jumper, so we'll set that at some specific height. Then you have your L. The L is the length of one rubber band. Right? And you'll have to measure that length and fill that in. G is obviously gravity, and mgh is your potential energy term. So if we look over here at our three columns, we have N, which is the number of rubber bands that we could potentially use, and it's gone all the way down to 150. We then have our equivalent spring constant, right? So if we can look at it in a minute. All we're doing is we're plugging in our K over here on this side, and then we go over here, and then we can set up an equation so that we can change K as we increase the number of rubber bands. And then this last piece here, you have the potential energy of the spring minus your potential gravitational energy, and we want this to be as close to zero as we can get. Now we could do this all out by hand, and it would take a while to finally get where we want to be. But here I've got a sample one for you where we've got some rubber band with a constant of 19.3, a mass of 70 grams, the height is 15.2, right? The length of the rubber band was about 9.5 centimeters, right? Gravity they used 9.8, and then they calculated that mgh, the potential energy, gravitational potential energy, is 10.4. So they plugged everything in, and most of this was actually done with just simple equations. So once we have the equation, it's really easy to get done. So if you look up here, we found that the equivalent spring constant was 19.3. And what they did here is up in the equation line, they took G4, which is our 19.3, and they divided it by B3, which was N. So when we take 19.3 divided by 1, we get 19.3. But if you look at the next one, now it's B4. So they took the 19.3 and divided it by 2. And as we go down, you can see how they're just always taking that 19.3 and dividing it by the number of rubber bands that you have in each instance. And the reason why the G4s don't change is because when you put dollar signs in front of the two cell locations, it locks those in place. So now what they did here in this for the potential spring minus the gravitational potential is they set up that equation of 1/2 kx squared minus mgh, right? And you can go through and you can look at all these different cell numbers and see what they did. So all it's doing now is it's pulling the information that we already have of C3 is our K, right? G6 is our height right here, and it's minus the length of the rubber band. Okay, so we have a good height of what the actual height is, the stretch, and then you've got that square term, and then minus G9, which is our mgh right here. And you can see that as they increase, or the K changes, right, we increase the number of rubber bands we get, the difference between the spring potential energy and the and the gravitational potential energy goes down. Now remember, our goal is to find when are they equal to each other, and that then means that we are right at the bottom, or we have the amount of energy that we started with is equal to the amount of energy that we're ending with. And if we go down to where we get 0, now we have a decision to make. Our iteration, our data says, all right, if we have 69 rubber bands, we're probably going to end up with 0.03 joules of energy. But if we go with 70, we're going to have negative 0.35. So here is where you need to think about what you're doing and make a decision in terms of, do I go with 69? Do I go with 70? Right? Maybe I go with a little bit less. Right? There are factors that error factors really that you may need to take into account. So look this Excel sheet over, see if you can try and figure out or try and have a good understanding of what is going on in these calculations. And now that you have an idea of what exactly is occurring in the lab, make sure that you have a good understanding so that when we start on Thursday, we can go right into it and we can get everything done in time. All right, so that's it. Feel free to stop by if you have any questions. If not, I'll see you Thursday.